you, Egita. Hello, everyone. Such a nice place to talk about an exciting topic, fusion. And you know, a few years ago, I was working in a totally different field. I was a manager in a corporate companies, and I was wondering, how could I combine my willingness to fight climate change and find a work that is compatible with it. And finally, I met the founder of Renaissance Fusion, and I became fascinated by this technology. So here I am in Riga, and it's an honor to be here. But before talking about fusion, I would like to talk about the problem we are trying to solve. And I chose two pictures to explain you that. First one, a thirsty man in India, where an extreme heat wave struck the country, 45 degrees in April. A second picture in Spain, here in Europe, a historical drought, the worst the country has ever faced in the last 50 years. So global warming is real. It's happening everywhere. We can feel it, we can see it. So we really need to stop emitting greenhouse gas emissions. 30% of the greenhouse gas emissions comes from the production of electricity. How come? Because today, still 2/3 of the electricity is produced by burning fossil fuels, coal and gas. So we really need to change the way to produce that electricity. So how about the demand? How about the demand? Let's think about the growing population. When I was a student, we were 6 billion people. We are now 8 billion people. Think about the change in our lifestyle, the creeping urbanization. Think about the electrification of the transport sector. The demand in electricity is expected to double by 2050. So to sum up, we must produce 2 times more electricity while targeting net zero emission by 2050. So we need a lot of carbon-free power plants. And this is probably why our governments are investing so much in renewables, solar and wind. But is that enough? Behind me is the city of Grenoble. This is the place where our company, Renaissance Fusion, is located. You can see the city lights at dusk. That would not be possible if we were powered with 100% solar energy. That would not be possible if we would be powered with wind energy. This is only made possible thanks to a non-intermittent electricity. Hydroelectricity and most likely nuclear fission. So I know nuclear fission is a sticking point in Europe. But what if there was another nuclear energy with the same advantages but no drawback? The Holy Grail of energy, fusion. So, as Egita said, this energy is carbon-free. It is available, non-intermittent, and can follow the demand. It is intrinsically safer than nuclear fission, with no chain reaction, no meltdown, and limited amount of waste. So what is fusion exactly? Fusion is a nuclear reaction in which 2 light atoms, usually isotopes of hydrogen, get to fuse together to form a heavier atom. And I'm sure you all know the Einstein formula, E equal mc squared, right? So what does that mean? It means that a difference in mass is energy. And we are lucky because in this reaction, the mass of the output is less than the mass of the input, so energy is created. And if you remember in this formula, c is the speed of light. It's a huge number. So it means that a small difference in mass generates a lot of energy. So to give you an idea, 1 gram of fusion fuel provides as much energy as 10 tons of coal. So great, let's just build a superstar on Earth. You might know these pictures from a movie. Well, that's not so easy. Why is that? Well, because in a star, gravity is acting. Gravity is gathering particles together so the reaction can keep going. But on Earth, the gravity is 28 times smaller. So we need to find some tricks to get good conditions on Earth. So we found 2 main tricks. One is to apply a strong pressure on a small target, a pellet. And we do that usually with lasers, for example. This is called inertial fusion. The second solution we found is to heat the fuel until it becomes a hot plasma, to circulate this hot plasma within the closed loop to favor the reactions. And we do that with magnets because we can't touch the fuel, it's too hot. This is called magnetic confinement. So in both cases, we must reach a temperature of 150 million degrees. So I know that might sound a bit like science fiction, but this is, believe me, this is very real. We have been making fusion for more than 70 years. So what's the problem? Why isn't that everywhere on Earth powering the planet? Well, because we haven't found yet a way to produce more energy out than energy in. This can be measured by a metric called fusion gain. It's written here, it's Q, right? Q is the ratio of the energy out on the energy in. So a Q greater than 1 means that we produce more energy, more electricity, than we consume. A Q less than 1 is the opposite. So typically, we want to be on the top right of this chart, where Q is greater than 1, right? Q less than 1 is on the bottom and on the left. And what we can see here with this chart is that we made continuous progress in fusion since the late 60s with the T3 tokamak in Russia to the jet reactor in Europe that almost reached Q equal 1. Q equal 1 is the first threshold. This is this orange banana here. Actually, we passed that threshold in December last year with a laboratory in US that reached Q equal 1.5 for the first time, for a very short time. But if we want a fusion power plant, we need a much greater Q. We need to reach a higher value, about 20 to 40. So this second threshold is called ignition. Ignition is what we want for a fusion power plant. Some of you may have a wood stove, and ignition corresponds to a moment where you don't need to light your fire anymore. The fire has taken and runs by itself. This is ignition, right? So where are we on the way to ignition and commercial fusion? Well, let's look at the European program. The European program is built on 2 international projects, ITER and DEMO. So ITER is a reactor that is being built right now in the south of France. It is supposed to reach Q equal 10, which means 10 times more energy out than energy in. So close to ignition, but not yet. So it will not produce electricity. And it will still be an experimental reactor. And the target is to reach that Q equal 10 only in 2035. So the next step is demo, the second reactor, a bigger one, a bigger reactor. This one will produce net electricity, but not before 2050. So now let's look at some other programs quickly. I will give just two examples. UK is probably one of the most ambitious countries. They have their own program. They target a STEP reactor, a reactor called STEP. They have already identified the site in UK, and they want this industrial prototype to be ready in 2040. Then if we look at China, China has rapidly caught up on fusion. They have their own reactor called EAST that made several records. They are now building huge facilities to develop fusion enabling technologies like magnets, heating system materials. And they have this project of a final reactor for 2035. But they only target a fusion power plant in 2050. So how about startups? Why would a startup work on such topic, such an endeavor? I mean, it's capital intensive. This is a long development. So why startup? I like to do a parallel with the space industry. Back in the 2000s, the space industry was the territory of the national space agencies, NASA, ESA, Russian agency, until SpaceX appeared. The objective of SpaceX was to reduce the cost of the rocket by a factor 10 and to improve the performance, in their case, reliability, by a factor 10. And they came up with that idea of the reusable rocket. So the goal of fusion startup is exactly the same. This is to reduce cost. This is to accelerate the development of fusion-enabling technologies for future fusion power plant. I mean, if you look at the program I presented before, the state project, they are all based on the same concept, the tokamak. Can we do differently? They are all targeting fusion power plant by 2050. Can we do earlier? So startups are here to challenge established orders and ideas. So we have a very rich ecosystem of startups in the world. When I say rich, not necessarily in terms of money, I will come back to that, but rich in terms of activity and ideas. So there are already 40 startups today targeting fusion power plants. You can see them here by country, by maturity. We have raised altogether 5 billion euros from private investors, among them Bill Gates and Jeff Bezos. And most of us target a fusion power plants by the 2030s. So many concepts are studied, not only the tokamak or laser fusion, but other magnetic confinement ideas, other inertial confinement ideas, and even hybrid ideas called magneto-inertial. So which innovation do those startups bring? Well, let's think first about what are the three main obstacles to commercial fusion. Number one, the materials. We need materials that can withstand the temperature and the neutron flux within the reactor. Number two, the manufacturability, the size. We need to reduce the size. Today, to reach ignition, the solution is to build bigger. Can we find another solution? And the third topic, remember the city lights. We need something efficient. We need something that can provide continuously electricity. And the problem is that today, most of the reactors are pulsed devices. They only create fusion for a few seconds. So obviously, I will not have time to present you all the different ideas from those startups. So I will focus on the startup in which I work, Renaissance Fusion. The number one thing, so materials, how to protect, how to find those materials. Well, the neutrons are hitting the solid walls, right? So you need to replace those solid walls very frequently. That's a problem. So the idea we came up with is, how about liquid metal walls? Why? Because that will protect the solid wall and avoid heavy maintenance. It will get heated by the neutron, so it can communicate the heat to a secondary system and create electricity. And on top of this, we can solve another problem of fusion, which I haven't talked about. The tritium, the fuel. The tritium is very rare on Earth. You need to produce it. And those liquid metal walls, when they absorb neutrons, they can regenerate the tritium, the fuel. The second challenge, the size. So how to reduce the size of the reactor? Well, we intend to use a material called HTS, high temperature superconductors. I will not detail that. But basically what you need to know is that with such material, you can double the magnetic field and apply a better pressure on the plasma. So by doing this, you can reduce the size of the reactor by a factor 4. And last but not least, remember the city lights. We need continuous fusion, continuous electricity. Well, at Renaissance Fusion, we work on the only concept that can provide continuously fusion reaction. This concept is called stellarators. That's the one you can see here. So we twist the shape of the plasma, and by doing so, we have a very stable plasma and continuous reactions. So the only drawback of this solution is that you need, as you can see, very twisted magnets. The magnets are here. So there have been already one experimental reactor. The most advanced one is there. It's in Germany. It's called Wendelstein 7X. But at Renaissance Fusion, we want to build the next generation of stellarator. But it needs to be easier to build. So instead of building a very twisted reactor, we intend to use regular cylinder. And instead of those very complex shaped magnets, we intend to use a laser engraving technique in order to create those magnets. So if you want to know more about this, please reach out to me. I will be very happy to help you, to explain you in more details. So finally, will fusion solve the energy problem? Well, the first thing I'd like to say is that first, it's on us. It's on all of us. I'm sure we all can do something to reduce our consumption on a day-to-day basis. That's the first thing I want to say. The second thing, I don't like to say that one technology is going to solve everything. That's not true. So we will need a mix of solutions. This mix of solutions will include renewables, will include fusion, will include fission, hydroelectricity, new energies, carbon capture. So that's a mix of all this. Now, will it be the energy of the future? Yes, I'm convinced about this. Fusion is already the most widespread energy in the universe. So I'm sure that it will become the energy of a sustainable future on Earth. Thank you very much. If you want to know more about fusion and about Renaissance Fusion, you can check our website. You can reach out to me. If you're interested in investing or joining us, we are hiring. So don't hesitate to contact me. Thank you very much.